So we discussed 8 basic properties, but I want to talk about 2 more that are a little more complicated. So I'm going to present them and then I'm going to do a proof. So if you don't care about the proof, you can stop after I talk about them. But you should care about the proof. You should. So the first one is that if some number C is a scalar, then the scaled version of the vector has the magnitude of the vector's magnitude times its scale, which I said that really poorly. But the idea here is that if I had a vector and it has some sort of magnitude, well, if I have 2 times that vector, it's going to have twice the magnitude. It's pretty simple, right? If I have 3 times a vector, it's going to have 3 times the magnitude. The tricky part here is that notice that's an absolute value of C, because if I have a vector in this direction, but let's say I take it -2, right? So I go not only in the opposite direction, I go twice as far. It's still going to have the same magnitude as if I went twice in this direction, which makes sense, right? If I travel 100 miles this way and I travel 100 miles this way, they're in different directions, but they're the same length. So the second one's, I think, is probably the trickier one, is that if I have a non-zero vector, so it's at least one of the components is not 0. Then then there's a vector u. I can make a vector u that if I take the original vector v and I divide it by its magnitude, or I multiply it times 1 over the magnitude. If I divide it by its magnitude, then that vector has length 1. So that is a unit vector. That means that u is a unit vector. What that tells me is that for any vector v that's not 0, because then your magnitude would be 0 and no, right? So for any non-zero vector, I can always make a unit vector that points in exactly the same direction. And that kind of makes sense, right? You know intuitively it has to be true that it exists, because if I have some sort of vector and it has some sort of length, there's always a vector that rides that line, but it stops at length 1. So this is a clever way to be able to construct that vector. Why would we want to do this? Oh man, why would we not want to do this? But anyway, so we're going to go to the proof portion. If you're done, you're done. If not, stick around. We're going to talk a little bit about this. All right, so if I have some vector v, and we're going to do this in the 2-dimensional case where v equals v1, v2. Well, then that tells me that CV is CV1, CV2. And that tells me that if I get the magnitude of CV, that's CV1 squared plus CV2 squared, which is C squared V1 squared plus C squared V2 squared. Well, they both have C squared in common, so we can factor that out. And if you remember your properties of square roots, we can split that off. Well, we know that that's just the magnitude of v. And the square root of a squared value it's not c. It's not. It's the absolute value of c. Right? Think about that. If c was -2, well, then -2 squared is 4. But the square root of 4 is +2. So you have to do the absolute value. Anyway, so that proof's done. This one's actually, the proof is easy if you accept what's happening. So we know that the magnitude of v is some number, right? It's just some number. We don't know what it is because, right? If I had an actual v with numbers, I'd know what it is. But anyway, so I have this. This is some scalar times some vector, right? So in this case, C is that scalar. So then the magnitude of U is the magnitude of CV, right? Where that's the C, because C times V. Well, we know that C is positive because the magnitude is going to be positive. So 1 over the magnitude is positive. So we don't have to worry about the absolute value. So that's 1 over the magnitude times the magnitude. Well, those cancel and get 1. So if that's causing you trouble, just kind of think about it. We're going to work an example. Maybe some real world examples will help. This is super important. So again, in a lot of real world scenarios, we want to take vectors we have and scale them down to unit vectors because there's a lot of really beautiful math that works for unit vectors, but it doesn't necessarily. But the math on it is kind of gross for non-unit vectors, or it's actually impossible depending on what you're doing. And so being able to scale vectors to unit values is just, I could talk all day about the importance. But anyway, those are the extra operations. We're going to do some examples.